Today, a variety of functional materials already enrich our society. The Division for the Molecular Design of Materials at the University of Tsukuba plays an important role in this context by analyzing the behavior of complex functional materials using advanced experimental measurements and theoretical calculations down to the atomic level. Using basic science to extract the fundamental unit or seed of a given material is of paramount importance to implement the desired functionality therein. We aim to create such material seeds to realize advanced functions with the minimum amount of atomic resources.
The Division for the Molecular Design of Materials is responsible for discovering such seeds of functional materials. Using the specific properties of elements, we aim to create new molecules that can be expected to exhibit desired functions and investigate their origins at the atomic level. In particular, we are focusing on the individual characteristics of specific elements from all over periodic table. This variety of element-specific features can be expected to lead to a huge variety of materials with tunable functionality. Moreover, we are interested in synergetic effects that may arise from a combination of specific properties of different elements.
As examples of research and development on advanced materials, we target an ultra-sensitive biosensor and an energy conversion system that is environmentally benign. The study focuses on the electron transfer between oxidoreductases and electrodes and aims to maximize the activity of the enzyme on the electrode. We are also conducting research on precise molecular assemblies by self-organization of pi-conjugated organic molecules, polymers, and biomolecules for optical or laser applications, storage, and sensing. For another example, during our efforts to generate pioneering new substances, materials, technologies, and concepts to contribute to the realization of carbon neutrality, we have synthesized the first example of a hydrogen boride, borophane, that make use of the specific characteristics of boron and exhibits excellent electron conductivity.
Our research group studies supramolecular chemistry. We design and synthesize unique macrocircuit oligomers and their transition metal complexes in order to investigate their functions. These molecules promise considerable potential for environmental and energy issues, not only for applications in sensors and separation materials based on molecular recognition, but also as catalysts for selective reactions based on their molecular capturing ability.
Another important issue is to replace the functions that are currently realized only by rare elements with those of abundant elements. For example, many catalysts that are currently used in organic chemistry still rely on the unique properties of transition metals.
What is important here is the responsible use of atomic resources. Looking at the element abundance ratio in the Earth's crust, 99.4% are made up of 15 major elements, such as oxygen and silicon. In other words, only approximately 0.4% are other usable elements, and they can thus be considered scarce. We investigate the replacement of rare and often toxic transition metals with other, more abundant elements such as silicon and aluminum. Furthermore, the creation of molecules based on such abundant elements may exhibit novel and desirable functions not found in transition metal-based compounds. We are actively engaged in the creation of new molecules, using the characteristics of various elements. In particular, the creation of compounds with unique structures, bonding modes, and electronic states such as pi bonds of heavier main group elements such as silicon. We aim to elucidate the photophysical and chemical properties of these new compounds, and thus develop conceptually new molecular transformation catalysts using abundant main group elements.